All right, welcome to 7-1 Day 2 notes. So first we're going to look at a sampling distribution. A sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. What's most important is where it says all possible samples of the same size from the same population, and that'll be kind of your clue that it's a sampling distribution. The population distribution gives the values of the variable for all individuals in the population. So below, we have an example of each. So we have the population distribution where we have 50-50 red and blue chips. And then we have the distribution of the sample data where we drew 20 chips at a time, counted the number of red chips that we have, found the proportion of red chips, put the 20 back in, remixed the chips, and then repeated the process many times. So in order to get a sampling distribution, we had to keep taking samples of size 20 until we got all possible samples. Right? Every single thing that was possible. And that's what's true about that sampling distribution, is that we're looking for all possible samples of the same size from the same population. So, one thing we have to keep in mind is that the distribution of sample data, of sample data, this basically describes individuals. Right? Each individual is representative of a dot on the dot plot, whereas a sampling distribution describes how a statistic varies in many samples from the population. So like in the example above, those are not individual people. All the p hats are individual, or all the dots are individual p hats. So they're all from the sample. So we're looking at a bunch of p hats versus a bunch of individuals. An unbiased estimator is a statistic used to estimate a parameter if the mean of its sampling distribution is equal to the true value of the parameter being estimated.
We're done.
A biased estimator occurs when the center of the sampling distribution is not equal to the true value of the parameter being estimated. The variability of a statistic is described by the spread of its sampling distribution. So, the spread is determined primarily by the size of the random sample. Larger samples give smaller spreads. So the spread of the sampling distribution does not depend on the size of the population as long as the population is at least 10 times larger than the sample. So again, that's that 10% rule. So will increasing the sample size eliminate bias? No. Right, you can never eliminate bias, so that answer is always no. But it will decrease variability. So sample size controls variability. If you increase the sample size, you decrease the variability. There's no way to ever get rid of bias once you have bias. All right, so let's look at number 3. So let's look at this survey on tall girls. So according to the National Center for Health Statistics, the distribution of heights for 16-year-old females is well modeled by the normal density curve with a mean mu equals 64 inches and a standard deviation sigma equals 2.5 inches. To see if this distribution applies at their high school, an AP Stats class takes an SRS of 16-year-old females at the school and measures their heights. What values of the sample mean X would be consistent with the population distribution being normal with a mean of 64 and a standard deviation of 2.5? To find out, we use the Fathom software to simulate choosing 250 SRSs of size n equals 20 students from a population that is n 64 2.5. The figure below is dot plot of the sample mean height of the students in the sample. So, is this a sampling distribution of X bar? So, if we look at this problem, it talks about they use the Fathom software to simulate choosing 250 SRSs. So that is not the entire population, since the population had 316-year-old females. So the answer to this is no. Remember that a sampling distribution has to be representative of the entire sample. So it has to have every possible outcome as a part of the sample. So the answer is no. This is not the exact sampling distribution because that would require a value of X bar for all possible samples of size 20. So this is what's called an approximation of a sampling distribution. All right, that's what we created there, is an approximation of a sampling distribution. If it doesn't say it's all possible samples, then you know that it's an approximation. And then we're going to describe the distribution. So remember that you describe the distribution using SOCS. So we're going to talk about the shape. So the shape is reasonably symmetric. And bell-shaped. The center is about 64. If we look at where the peak of this is, and if we go straight down, you can see it's right about 64. .64 inches. And the values vary. So this is the spread from, it looks like 62.4 to, we go to where the highest point is, about here. So 65 point, let's go with 7. Okay. And then there seem to be no outliers. Right, it doesn't appear as if anything is really that far from the mean. Alright, so again, SOCS comes in handy again. You can see the shape, center, spread, and then outliers. So we're going to make a graph of the population distribution. So in this case, the population distribution is talking about the height of the 16-year-old females. So because it's the population distribution, remember that we're talking about each individual. So that's talking about like a histogram. If we were talking about make a graph of the sampling distribution, then we would make a normal curve. But because this is a population distribution, we're talking about the individuals, we're going to make a histogram. So we're going to go from about the smallest, so 60, and we can go up by about 1.5. Should be 70.5. Okay, that should be good. And then on the along the bottom, we're going to put heights of 16-year-old females. So remember, you always have to label, and this is in inches, so we always put it in parentheses. And then over here would be the frequency, since this is a histogram. So we need to go up 0, 1, 2, 3, 4, 5, 6 should be about good. And then we just count how many people we have between 60 and 61.4. So that would be just 1, and then keep going, and that would be 4. So just like we did back in chapter 1 or chapter 2. We're going to go up to 6. Oops. Try to make them a little bit straighter than I am. And then we go to 4 again. And then 3. And then 1. And then we don't have anybody in between those values. And there we go. So there's an example of a histogram. And then again, we also make sure that you have your labels. So number 4, cold cabin. The Fathom screen shot below shows the results of taking 500 SRSs of 10 temperature readings from a population distribution that's in normal within 50 and 3 and recording the sample minimum each time. So describe the approximate sampling distribution. So again, we're talking about socks. So the shape appears to be approximately normal. Or you can say reasonably symmetric. So I'm going to put approximately normal. Right, the center. So we look to where the center of the distribution is, where the peak is. Go straight down. You can see it's somewhere about 45. degrees Fahrenheit. And let's see, the values vary. So the spread values vary from the min to the max. So really we're kind of like talking about the range. So it looks like 39.2 to 50.1 degrees Fahrenheit. And then outliers, there appear to be no outliers. Alright, and then part B, suppose that the minimum of an actual sample is 40 degrees Fahrenheit. What would you conclude about the thermostat manufacturer's claim? So if we look at where 40 degrees Fahrenheit occurs, so 40 degrees Fahrenheit is here. If that were to be the center of the distribution, right? If that were actually true, how many of them are less than that? Only 1. So again, we're talking about the probability of it being 40 is so low that this is not at all what we expect. So we're going to write down that a sample minimum of 40 degrees Fahrenheit is quite low. Like in our case, 1 out of 500. This suggests the manufacturer's claim is false. Right, because the probability of it actually being 40 degrees will occur only 1 time out of 500 different samples, when the true mean was 45. All right, number 5. A statistics teacher fills a large container with 1,000 white and 3,000 red beads from the mixes, and then mixes the beads thoroughly. She then has her students take repeated S or S's of 50 beads from the container. After many S or S's, the values of the sample proportion p hat of red beads are approximated well by a normal distribution with a mean of 0.75 and a standard deviation of 0.06. So what is the population? So the population are the 4,000 beads. The population distribution, remember population distribution is talking about the individuals. So 1,000 beads are white. And 3,000 are red. Okay, part B, describe the sampling distribution of p hat. How is it different than the population distribution? So if we're looking at the sampling distribution of p hats, we have to do the shape, center, spread, outliers. So again, socks. So that's what we're doing here where it says describe it. So the shape. They tell us that the shape is approximately normal, approximated by a well-normal distribution. So we're going to say approximately normal. The center, because this is a sampling distribution, the center should be approximated by where the p hats are. So the center mean equals 0.75. The spread would be the standard deviation. It's about 0.06. And then there are no outliers. How is this different? Because remember that the population distribution is about the individuals, and the individuals were the types of beads, which is categorical. Whereas the sampling distribution, we just wrote down the mean, so we have actual quantitative data, right? And the measurement of the amount of beads that there are. So the mean, or the mean of the proportion. So the population distribution is categorical, right? It's either categorical, I messed that one up. Whereas the sampling distribution is numerical value. Right? Remember that the sampling distribution of p hats is the mean of all of the p hats. Those are all measurements. Whereas the population distribution is a color, red or white. So number 6, just before a presidential election, a national opinion poll increases the size of its weekly random sample from the usual 1,500 people to 4,000 people. Does a larger sample size reduce the bias of the poll result? So again, big fat no, because you can never change bias. Sample size does not affect bias. Right? You're not ever changing bias. So anytime you have that question, it's always no. Does it reduce the variability? The answer is yes. Increasing sample size reduces variability. One way to explain is if you just think of the formulas. So think of the formulas for variability, which would be standard deviations. Each of those formulas are divided by n. So as n increases, and you divide by a larger n, the quotient, right, the result, is smaller and smaller. So a larger sample size will reduce the variability. So more people means more information, which means less variability. All right, number 7, a study of the health of teenagers plans to measure the blood cholesterol levels of an SRS of 13 to 16-year-olds. The researchers will report the mean X bar from their sample as an estimate of the mean cholesterol level mu in this population. Explain to someone who knows no statistics what it means to say that X bar is an unbiased estimator of mu. So if we choose many samples, the average of the X bar values from these samples would be close to mu, right? The sampling distribution of X bar is centered at the population mean mu we're trying to estimate. And then part B, the sample result X bar is an unbiased estimator of the population mean mu, no matter what size SRS the study chooses. Explain to someone who knows no statistics why a larger sample size gives more trustworthy results than a small random sample. So a larger sample size will give more information and therefore more precise results. So the variability in the distribution of the sample average decreases as the sample size increases. All right, so in case you're not going to be here tomorrow, here's our assignment down here. Again, it's still in 7-1, so the page is on your guide, but if you flip to the end of section 7-1, the problems are there, and work out 9, 11, and 13, and then 17 through 20 are multiple choice. Let's change this, though, before we go on. So let's just do 17 and 19. And then won't worry about the multiple choice. So do 9, 11, 13, 17, and 19. We actually did number 20 in class and number 18 in class as well. So, yay.